Hi, my name is Udo's Lender. Welcome to my YouTube channel about adventures in astrophysics. Quasars are the most luminous objects known in the universe. The term quasar is an abbreviation of the phrase quasi-stellar radio source, as they appear to be star-like on the sky. In fact, quasars are the intensely powerful centers of distant, active galaxies, powered by a huge disk of particles surrounding a supermassive black hole. As material from this disk falls inwards, some quasars, including the twin quasar, fire off superfast jets into the surrounding space. When the first were identified, 60 years ago, they were mysterious objects, with unbelievable distances, much farther away than any known galaxy at that time. The extreme distance also means that they existed long ago. Indeed, they are so bright that we can see them across a distance corresponding to most of the history of the universe. This video is about a remarkable specimen from this class of objects.
QSO 0957 plus 561A and B are the two components of a double-imaged quasar in the constellation of the Big Dipper. Here, a concentration of mass on the way to us causes the light to bend so that two images of the quasar appear in the sky. The phenomenon is called gravitational lensing and is a consequence of Einstein's spacetime curvature.
More details about gravitational lensing in another video on my channel. The twin quasar was discovered in 1979 by an Anglo-American team led by Dennis Walsh, Robert Carswell and Ray Wayman using the 2.1-meter telescope at Kitt Peak National Observatory in Arizona. The team noticed that the two quasars are unusually close together and that their redshift and spectrum were remarkably similar. They published their find with the hint that they could be two images of the same object, created by a gravitational lens. The quasar is located 10 arc-minutes north of NGC 3079 in constellation Ursa Major, behind the Big Dipper.
The departure of light from a straight line, caused by the huge mass of the intervening galaxy cluster, is not so much the result of a curved space, but the result of a drop in the speed of light. It is slowed down in the presence of a gravitational field. The gradient in this field causes the observed bending primarily. Einstein had described the effect as a consequence of his 1916 general theory of relativity, although in a 1936 paper he also predicted, of course there is no hope of observing this phenomenon directly. However, critics noted a difference in the appearance of the two quasars on radio frequency images. In mid-1979, a relativistic jet emerging from quasar A was discovered at the Very Large Array near Socorro, New Mexico, without showing a counterpart in quasar B. Also, the distance between the two images, at 6 arc-seconds, was too large to have been caused by the gravitational pull of galaxy G1, identified near quasar B.
It was discovered shortly thereafter that the galaxy G1 is part of a galaxy cluster, which amplifies the gravitational distraction and can explain the observed distance between the images. Finally, in 1983, a team led by Mark V. Gorenstein observed essentially identical relativistic jets on very small scales from both A and B using VLBI. VLBI stands for Very Long Baseline Interferometry. Here the interconnected telescopes are not just a few kilometers apart as with VLA, but on different continents and thus achieve a much higher resolution. This technique, also used to take first pictures of black holes in the centers of galaxy M87 and our own galaxy, is described in detail on my website under the heading How to Take Pictures with ALMA, Part 1 and Part 2.
The difference between the large-scale radio images is attributed to the particular geometry required for gravitational lensing, which is satisfied by the quasar, but not by all of the extended jet emissions seen by the VLA near image A.
We can estimate the redshift of the quasar ourselves, using data from the SDSS. How this was done is explained in another video on my channel.
From the spectrum of the quasar we derive a redshift of Z 1.41 corresponding to 9.2 billion light-years. We used the light travel time and standard cosmological parameters. The lenticular galaxy is found at redshift Z equal to 0.35, corresponding to less than the half distance. The lensing galaxy, with a small apparent size of half an arc-minute, is nearly aligned with the B image and offset by 1 arc-second. Given the large distance of the quasar, it would be a coincidence if other galaxy clusters were not crossed on the way to us. In fact, others have been found with redshifts of 0.5 and 0.9.
The two images of the twin quasar are separated by 6 arc-seconds. Both images have a comparable brightness. The A component shows 16.7 mag and the B component shows 16.5 magnitudes. There is a time lag of 417 days between the two images.
The galaxy G1 appears with 22 mag, 1,600 times fainter than the quasar. But partly this is an amplification by the lens effect.
This lens system was observed in all wavelength ranges, from radio to X-rays. The two images of the quasar are very similar at all wavelength as they should be.
Slight spectral differences between quasar A and quasar B can be explained by different densities of the intergalactic medium in the light paths, which lead to different extinctions. They are nowadays also interpreted as microlensing effects and allow to study details in the innermost structures of the quasar, such as the accretion disk, the magnetic field and the jets. Based on many years of observations, Rudy Schild of the Harvard-Smithsonian Center for Astrophysics casts doubt on the existence of a supermassive black hole at the center of the quasar. Instead, an exotic, magnetospheric eternally collapsing object, or MECO for short, is to take its place. More about this in Wikipedia. Here are the objects in the environment, contained in the Simbad database. For the currently blinking cursor, the footer is highlighted. Well, what's awesome about the object now?
You must see, it was the first to be discovered. Before that, gravitational lensing was just theory that few people thought about.
It is also important that the runtime difference of 417 days was found.
Then it is one of my favorite objects. 20 years ago, I took this picture with a small telescope. Amazing how little it takes to prove the distortion of space and time, caused by the gravitation of a galaxy cluster and the enormous light amplification of the distant object. Imagine, when this light had traveled half the way to us, our Sun and Earth were just forming. Watching all this, with your own telescope, watching general relativity at work. That is really awesome, isn't it?
For the many high-resolution images in this video, we must give credits to the Hubble Heritage Project. This video was brought to you by gigaparsec.de. If you liked it, give us a thumb and subscribe to our channel, Adventures in Astrophysics.